This is project 3.2, Chump, Code, Clock, and Counter. For this project today, we're only going to be looking at two parts of this setup. The first being this breadboard, the clock, and this section here for the program counter. There are other chips not connected to anything because this is just for planning for the future when building the computer, so I don't have to rewire the program counter, and it just makes the most optimal sense according to the image on Mr. Darcy's website. So let's start with the clock. This is the clock module for the computer. The clock controls how fast it computes things. So this potentiometer can be used to control the speed. If I turn it right, you can see it is currently going too fast for the camera and my eyes to see, but it is flashing. And if I turn it to the left, it's gonna slow down until it gets pretty slow. So there are two modes on this clock. This that I just showed you is automatic, and that is produced by this 555 timer using the oscillation function. And then there's also manual mode, so we can use this switch to toggle back and forth. And manual mode will bypass this and take an input from this button, and that will advance the clock 1. So when you have a button and you press it, sometimes it can contact a few times because it's mechanical, so we do something called debouncing. So this is a debouncing circuit, and it's basically made to eliminate a ripple effect. So that's like not a clean square wave and make a clean output. So then the clock signal is fed through the 74LS04, the 74LS08, and the 74LS32, and at the end of that, these are all logic gates, and at the end of that, the clock comes out of here and it goes up into the program counter. An interactive clock module that I recreated in Tinkercad circuits. So you can actually put all your components on the breadboard, and it knows how each individual IC and component works. So what's really cool about this is you can start a simulation, and then you can actually prove that it works. Bear with me for a bit because my computer is a bit laggy, but as you see, I press this button and this LED just lit up. So we can also go to the automatic clock pulse and they'll start blinking. So the next part of this project is the program counter, and the backbone of that circuit is the 74LS161 4-bit counter. So basically it has a total of 4 internal flip-flop gates, and the inputs of all of these are synchronized to this clock signal so that it makes all of the gates synchronized. So this counter starts from 0 and incrementally counts up towards 15, so 0 is 0, 0, 0, 0 in binary, and 15 is 1, 1, 1, 1. So it counts up from 0, 0, 0, 0 to 1, 1, 1, 1. So after it finishes the counting, the cycle is reset and it starts at 0 again. So there are two functions that can either be controlled automatically or with buttons. So the first one is load, and that is to load the values from the input. So here, in the first mode, it is done automatically through this NAND gate using transistors. So this gate was chosen instead of the SM74LS00 chip because I was only utilizing one of the gates, and I thought having a three gates not being used was a waste of space on my breadboards. So I created a NAND gate with 2 transistors, and it functions the same from the testing that I've done. That loads the values, and there are also 2 modes. So this switch can be used to toggle between automatic or the manual with the switches here. So you can input a value and the LEDs will turn on. This is my code for the Chump. So over here, this is the high level, machine level with the address and instruction. This is the Chump assembly level, and then this is the comments on the side. So let's start with the address. So this counts 0 to 15 in binary on this side. And then this is the high nibble and the low nibble. So this is the instruction, and then this side here is either the constant or memory. So yeah, that's my program.